All right, that's a great part of finally being in person for those of us in the room, right? Lots of opportunities to share lessons learned, and that is the topic of this next session. I'm Renee Spenst, I'm with Ducks Unlimited, and we have three wonderful speakers here to talk about design and engineering advances to support nature-based adaptation, to really think about how we can get to our shared resilience goals around San Francisco Bay. And here comes the third. So starting with Steve Carroll with Ducks Unlimited, and I'll introduce each speaker as we go.
Thank you very much. Let's see if I can move this along here. This is a different slide deck, isn't it? I'll just move forward. Oh, beautiful. Look at that. Okay. Well, thank you for this opportunity. I appreciate being able to share my 2 cents with everybody in the group. I think there's abundance of design guidance for our traditional structural ways of protecting the shoreline, right? We've been doing that forever. It's well documented. We know with pretty good certainty how it's going to perform once we put it in place. It's not the same with these designing with nature-based solutions. There's still a lot of judgment that goes into designing these restoration techniques, and that judgment really manifests itself into some uncertainty exactly how these are going to perform once we put them in the ground. There is obviously, this workshop's one example, a lot of great interest of developing that body of knowledge and moving forward towards having some good concrete design guidances that could help us out. And in fact, a few years ago, the American Society of Civil Engineers teamed up with the Corps of Engineers, several universities and other organizations, including Ducks Unlimited. And the whole intent of that coalition is to provide discrete design guidance to practicing engineers that they could help pull these nature-based tools into their standard way of doing shoreline resiliency work. And I'm not talking just marsh restoration type of work, but highways, everywhere that we're working where we actually interface with our stuff. So I think, until that comes to fruition, we need to move forward, do what we have with the knowledge we have, and pull our lessons learned forward. And then we will, have to be prepared to do some adaptive management. We can't let the perfect be the enemy of the good. It's kind of interesting ambiance we got going here. And we'll get, we'll do what we can. Let me just move along here. Being that this is a design panel, I kind of felt that I needed to put in some design parameters. And these, I think they speak for themselves. They're pretty straightforward. I'm not going to really talk a lot about them, but just a couple I'll speak to. But in general, where we work does make a difference in what we can do and how we do it, right? If we're working in fallowed ag lands that have been, we're in production for 100 years and we're adjacent to uplands and other wetlands, and we got a whole different approach than if we're working in an existing tidal marsh up against the aging levee that protects, flood protection for residences. How we go about that, our risk level that we're willing to take, will also feed into the amount of nature-based stuff that we're wanting to put in there. We're going to have to make some evaluations. We got a big scale of work that we have coming up that we have to do, and so we have to decide where we want to focus our efforts and where we just need to kind of protect and hold the line, or maybe there's a combination of the two in there. Obviously, sea level rise is one of the major drivers, one of the major parameters that we're dealing with. Ducks Unlimited typically uses the Ocean Protection Council projections that they came up with a few years ago. I'm sure everybody here has probably seen this. The blue line is the Paris Climate Accord. We're going to do some reduction in greenhouse gases. The red line's kind of status quo, move on the way we've been doing things in the past. And then the purple line is, all hell breaks loose. We have ice shelves sloughing off from Greenland and Antarctica and everything like that, which if you look at the news, kind of maybe that's the track we're on. But we're pretty optimistic, and we're going with the red line, the kind of status quo. And depending if we're working on a project that has flood protection elements versus more marsh migration habitat elements, it'll tell us where we're going to go within that band of uncertainty there. Jeremy Lowe gave a tour a few years ago, and he handed this out, and I thought it was a very elegant way to present the risks that we have coming up, or challenges that we're coming up. And so if you look at this chart, at the bottom line, it's basically the average tides at San Francisco Bay, and then it transgressions into sea level rise progressions. And then the stars that are above it, or the pluses, those are the maximum monthly tidal elevations. And that's kind of our flood control elevation, right? That's what we're protecting against. And that too follows the sea level rise projections out. The red line that goes across represents our current flood protection level. And this starts in 2000. And if you assume that we don't do anything to improve our flood protection levels, and you also assume that we're going to maintain what we have, which maybe is a pretty big assumption, as you move forward, you start with a 100-year flood protection level, but by 2033, that drops to a 20-year protection level. And going out to 2060, now you're at a 2-year event. Every other year on average, you're going to have flood issues, right? I mean, that's kind of shocking. And if you couple that with the Coastal Conservancy and Valley Water and the Corps are doing at the South Bay Shoreline Project, where they're doing about 4.5 miles, I think. And it's a huge effort, bringing in 1 million yards of dirt to rebuild a whole flood control levee with ecotone, a lot of other elements for infrastructure, but that's $500 million. And what's that, 1% of the perimeter of the San Francisco Bay? I mean, it's a daunting challenge, right? And so I think designing with these nature-based solutions may help stretch our resources and help us do more with the limited amount of stuff that we have. And dirt. So obviously we need dirt for marsh migration areas, and the type of dirt that we get really does make a difference, right? It has to be clean. Obviously, we can't have something that's toxic to the aquatic environment. It has to be a suitable growing medium, but it also has to be somewhat resistant to erosion. So that means we're going to fall in a cohesive type of soil, which is a clay or organic silt, something like that, right? The sands aren't quite appropriate for this type of restoration. And those cohesive soils have a different sediment dynamics than our sandy beach processes. They kind of bond together at a molecular level. And so it takes the wave impact to dislodge the particles, and those particles are really fine. So once they're up in suspension, they tend to be migrated away from the site. So if you look at the bottom photo, that's a picture of Sears Point after a scarp had started to erode, and you can see that the near shore is etched. That's because those fine sediments are being picked off the near shore, and it's going down in elevation. And as that happens, now you have larger water depth limited waves that are able to propagate through there and impact that scarp, and eventually you'll start marching that scarp backwards inland. And protecting that near shore from going down is important, because the wave energy is proportional to the square of the wave height, which means if you have like a 1 foot wave and it goes up by 1/10 of a foot, you got about 20% more energy in that wave that's impacting that shoreline. So it's important that we try and protect those near shore areas. And I think nature-based solutions are one way that we could do that. So what kind of tools do we have in our nature-based toolbox? There's a couple different approaches, I think, that we could look at. And one is just increasing the erosional resistance of the area itself. And vegetation is like, well, a really good way to do that, because the aerial portion of the plant tends to attenuate waves. It also has the ability to try and trap sediment. The roots tend to lock in the soil that's already there. That's not always the case. At Elkhorn Slough, they have a tidal zone, the intertidal zone, that really doesn't have a lot of vegetation down there. So they have to have a different approach. And maybe another approach is a gravel filter or a gravel beach. And with that approach, you would take increasingly larger sized gravel sands and build it up to a point that it might get picked up by the tide when it impacts the wave, but it's dropped back out when the wave recedes. And that way you provide a buffer between the fine grained soils and the wave energy. And then of course, there's various ways to attenuate waves, right? We can raise the marshes in front, put out barriers, that type of thing. But another thought is just a hybrid approach, right? We can't always just do a structural. We don't always want to just do a nature base. So maybe we want to combine the two. And reef balls and barriers like the giant marsh castles there is one way to do that. So where do we get the sediment from? If we're lucky, we have enough space, we can borrow it on site, right? There's a lot of advantages to borrowing it on site. You can construct habitat features with the excavation and then you place it where you want it. You're totally in control of your schedule. The disadvantages are one of the time, you get the soil that's there. It might not be the right soil that you want, but that's what you have. And you might not have the soil in the quantity that you want. So you may wind up excavating more of your marsh, your future tidal marsh than you want to, just to create the soil. And then you have more open water areas that are less marsh and potentially more wave impact areas. Another option is import. And to say that it adds complexity is actually kind of an understatement. Material for import can come from desilting projects, right? That's usually more of a granular, sandier material. And it's not a huge volume, but it is important to reuse that material. Dredged material is also another viable source, but that's only so much dredged in the San Francisco Bay Area. And there's a lot of competition for it, and it is difficult to get it to the site. And when it comes in, it's usually pumped in fluid form. So it's kind of probably generally better off for use for generally raising the marsh elevation, but you can dry it out and repurpose it. But most of it comes from commercial development sites. And that you're losing control of your project because you're linking your project with other external projects. So now they're in control of the timeline and their objectives are completely different than our objectives, right? Their time is money. They want to get rid of a waste product, and that waste product is what we're trying to get. And they would rather just pay money to move it off than to wait and work with us in order to bring it into our sites. So it's really challenging. And also a lot of times the material that we want to bring in, that time they're offholing overlaps with windows for sensitive species, special status species. So we're not able to actually bring in the material when we want to. And so then we'll lose the material that way. Material that comes into our sites has to fall under a QAP, which is a good thing to QAP. Make sure we bring in clean soil that's not adversely affects our site. But it is another process that's a complicated process and it does take time. And so there's a very extensive list of criterion that you have to test for. And usually the source sites don't want to spend the time to test around and do a lot of different tests and various steps and all that. They just want to take a few basic samples and figure out where they're going to take the material. Almost every site, I'd say probably every site has material that will not meet our screening criteria. So unless you can get to where you segregate the site at some point, you're not going to get any material. And then if you do get the material, there's a process where you get the test results go to a independent reviewer, a quality assurance officer that looks at the material. If they think it meets it or if it's close, they might send it to a third-party reviewer, and then that goes to the water board and BCDC for their evaluation review. That all takes time, and sometimes we've lost material just because the source site wasn't patient enough to wait for that process to go through. So there's a lot of challenges with that. I got 3 more slides, and they're going to kind of talk more about lessons learned with the projects we're currently working on. Hopefully I don't sound like I'm just bitching too much, but this slide represents the South Bay Salt Pond. That consists of Ravenswood, Mountain View, and Pond A8, which are Don Edwards National Wildlife Refuge ponds, and then Eden Landing is California Fish and Wildlife Pond. And all 4 of those ponds are actually trying to actually bring in material in order to do their restoration project. So there's already competition amongst those 4 sites themselves, right? And the model that we've been using is a dirt broker model where there's contractors out there that try and source this site, and then they'll bring it to us and we get it at no cost. So if you look at that construction triangle where you have money, you have quality, you have time, we're picking the money and the quality and they get the time. So we have to wait for them to find something. But for them to bid on this work, they need a certainty that they'll have a place to go. So each one of these sites, we've obligated to an individual contractor for them to go look for material to bring it in. Ravenswood, it happened to be is the one that was closest to restoration. And we were at a point where we just need a few thousand more, 30,000 more yards. It's a lot of material, but not a lot in the grand scheme of things. And we had material going to other sites because those contractors were being successful, but the one that had you want to say ownership of Ravenswood wasn't getting any material. So we just were sitting there with nothing to go, which was very frustrating. And then in 2022, we had a few issues where We had material that was ready to come in, but we didn't meet the whole QAP process timeline, so we lost it. We had material wanting to come in, and we had a lot of endangered species. This chart here shows all the circles are snowy plover nests. They move around. We would issue these every week, and so the contractor could see where they can and can't move, and it could change daily. We had biologists out there daily watching over it. So we had to stockpile material on site, which meant the project now had to pick that up at a later date and move it. And at the far end of the site where you see the small chunk of red, that's a canal that we've been building up. There's ridgeway rails out there that have pretty much precluded us working there until after September. And there's very little material coming in after September. And we were trying to get the job done last year. So when we had some material available, we overloaded it. We exceeded our geotechnical guidelines that we had for the project, and we caused this levee silt flares that you see there. And it caused us to wait a year, but if we didn't try that, we would have been waiting a year anyway. But we did have to take some corrective actions in order to make that amended. Sears Point is another project that's located up in San Pablo Bay. It's on fallowed farmland, a subsided farmland. It's, if you look at it, it kind of looks like a fish, and the spine of the fish that goes along the railroad sign there, that's actually where we built a new setback levee so that we could restore the tidal marsh area. And that levee is about 2.5 miles long. It's about 1 million cubic yards. The material for that levee was borrowed from on site. So you can see the tidal channels going through the graphic there. Those are oversized so that we can generate the material that we needed on site. The levee itself went along varying depths of young bay mud. So the levee height was built to different elevations in hopes that once it's settled, it would kind of settle out to the same level of flood protection along its length. It was built in 2 stages. The first stage went up to about elevation 10. That included the habitat transition slope that you see moving out into the marsh and the little inset. And then on the backside, it included a stability berm that kind of helped stabilize the foundational soil so we didn't have a levee failure. And then the next year we came back and we raised it up the rest of the way. The habitat transition slope on this one varied between 10 to 20 to 1. So you can see there's kind of like a scalloped line that goes along there. And then there were some marsh pans that were installed along the 20 to 1 slopes along there that you can see. It looked like little kidney beans or so in the graphic. In addition, we put a bunch of marsh mounds out in the middle of the site, which are the circles you see. There's about 500 of them. They were just built up as quickly as we could to kind of get more. We went for quantity over quality. They were just mounted up without any real compaction requirement. And they were hoping to break up some initial wave and provide some areas for vegetation to get established. It can maybe be a nuclei in the future to move out into the pond. So it was restored 2015, and around 2018, a scarp started to develop. And I'm going to leave it there because I think Stuart might be talking a little bit about that. So my last slide, Cullinan Ranch, and that's also up on San Pablo Bay. And we've took a few different approaches at Cullinan Ranch. And I think one of them was we built a setback levee on the far east side. That was an area where we mined material from within the site. We knew we were going to backfill it. The material turned out to be really acidic. It was fine from an abatement standpoint, but we couldn't get plants to grow. So we had to come back in and do a substantial amount of amendments and treatments in order to get that to be suitable for vegetation. On the other one, on the far left side of the screen, is Pond 1. That's about a mile-long levee. In about 2018, about the same time that Sears Point got to scarp, that one started a scarp that progressed very rapidly back to the edge of the shoulder of the levee. And we were afraid that we were going to lose it. And since it was a difficult site to get to, we decided to come with a hybrid approach. We brought back in some fill, brought back in riprap. We armored the site, and then we buried the riprap, filling the voids of the riprap and putting soil over the top, and came back in and did a pretty massive vegetation effort with aquatic and upland plants. And in 2023, we just took these photos. There's areas where there's still mud flat and it looks just like we built it and walked away. There's areas that are fully vegetated, and there's areas like this where you have some of the rock has been etched away and you can see it, but the dirt is still within the rock voids, and we still have a lot of vegetation there. So hopefully this will start trapping sediment and accreting and filling in on its own. So thank you very much. Appreciate your time and attention. And next.
just a moment to switch the slide decks. Cheers. All right. And here we go. Almost there.
Thank you so much. All right. Oh, good. This mouse kind of works. Folks can see my pointer. I'll be pointing to things now and again. Hi, good morning. My name is Gavin Archbald. I'm an associate restoration ecologist with Harvey Associates, and I'm really grateful to be here today and talk with you. The title of this talk is Transition Zone Design is Context Specific, which I think Steve's talk just alluded to. And then I'm going to present some lessons from two different South Bay flood risk management levee projects. And I'm starting off here with a photo of a California Ridgeways rail that's been pushed out of the marsh by an extreme high tide and is pretty exposed to predators in this kind of a situation because the transition zone isn't sort of adequately vegetated. It's also quite narrow and steep. So just sort of highlighting the importance of the transition zone for Ridgeways rail. So I'm going to start off by talking about, in general, the ecological functions of a tidal terrestrial transition zone or transition zones in general. And then I'm going to provide the context for two specific projects that Harvey Associates has been collaborating with others on that's led to two different transition zone recommendations or recommended designs. Those are the two projects shown here, both in the lower part of South San Francisco Bay. And then after talking about some of the functions and values of T-zones, I want to circle back to touch on some of the limits of constructed transition zones to sustain marshes with sea level rise. And first off, just sort of a definition, when I'm referring to the tidal terrestrial transition zone for this talk, I'm really referring to the suite of habitats or the space between the high elevation tidal marsh and the adjacent upland. And when we're thinking about restoring the space, we're often thinking about what are the types of habitat functions, what are the functions that we want to recreate in this space. For example, habitat diversity, habitats like salinas and alkali meadows and seasonal wetlands were historically present and can be restored. Transition zones provide a buffer for the marsh from upland land use, and marsh vertebrates using the marsh can use that refugial habitat within the transition zone to, for cover during extreme high tides. This also provides some sea level rise accommodation space and, flood protection advantages. There are other functions too, but I wanted to highlight some of these. And historically in the lower South San Francisco Bay, the historical transition zone, as shown here by SFEI, was quite broad and diverse. In some places it was miles wide. So the tidal marsh is sort of this color, and the transition zone space are these other colors. You can imagine in that kind of a landscape with sea level rise, marshes can migrate and move upslope, and there's a large space to accommodate that change. By contrast, today we filled up to the edges of our marshes and into our marshes. We've lost, excuse me, we've lost a lot of that valuable transition zone habitat, which you often see in the lower South Bay, where the transition zone is a really narrow little strip between the marsh and adjacent upland. And so we've lost a lot of those functions, and therefore restoration of the transition zone is an important part of the tidal marsh recovery plan for the salt marsh harvest mouse and the Ridgeways rail and other species. But I think, as Steve just explained, a whole bunch of different ways that they're building transition zones. One size doesn't fit all. And when we're talking about the slope of the transition zone, the target habitat types, the construction methods, they're all context specific. So for this talk, I wanted to just maybe throw out a sort of a framework for thinking about transition zone design in terms of what are the functions that are needed, and among the different design options, what's going to provide the greatest ecological lift. That's often the lens that we use to think about transition zone restoration design. The first project, I want to give an example of that for is the South San Francisco Bay Shoreline Project. This is being implemented by the U.S. Army Corps of Engineers. It's a 5-mile flood risk management levee system shown in teal green. And this project includes permitted 30 H1V transition zones or ecotones. They're sometimes called along ponds A12, A13, and pond A18. Reaches 1 through 3 are currently in construction. And our firm's been collaborating with an engineering firm, Schaff and Wheeler, and closely with the California State Coastal Conservancy to develop a basis of design for these transition zones, which is contained in a report. And now we're in the process of sort of modifying that design as the construction process unfolds. And in terms of the design drivers for this transition zone, one is the CEQA-NEPA document that describes really quite generally what this habitat will look like. It calls for a continuous, gently sloped 30H to 1V transition zone, restoring a diverse native habitat mosaic representative of historical transition zone habitats. So there's a lot of space to design within that general description. And from a restoration standpoint, the great promise of the San Francisco Bay Shoreline Project, in addition to providing flood protection for the adjacent communities, which is a hugely important component, it's also going to create the opportunity to do some large-scale restoration. About 90 acres of transition zone are called for in the project permits. And then once that flood risk management levee system is in place, the outboard ponds will be able to be breached and marsh can be restored in collaboration with the South Bay Salt Pond Restoration Project and those outboard ponds. And I'm showing you here sort of an idealized future vision of what those restored marsh complexes might look like. The 3,000 acres is a pretty big chunk. Currently, though, once these ponds are breached, they're going to be open water. These are former salt ponds, they're subsided, and it could take decades for them to accumulate enough sediment for tidal marsh vegetation to recruit into these ponds. And so in the meantime, we're concerned about the effect of wind wave erosion on the transition zone slope. And this is the current situation out at pond A18, which is, rock. We're not going to rock our shoreline. We need a nature-based solution here. That's one of the design drivers. Another design driver is the way that the earthwork for this project is unfolding. So the flood risk management levee footprint is shown here in orange along pond A12 and A13. And this is a cross section of the flood risk management levee. In order for the Army Corps to construct this levee, they have to cut down through bay mud and put the levee on firm alluvium, and that's generating about 200,000 cubic yards of bay mud from the footprint of reaches 1, 2, and 3, which are being stockpiled here in pond A12. And the project has long envisioned taking that bay mud and reworking it into that transition zone slope. When we look at the cost to do that, to do water, and to do the earthwork, and by we, I really mean Schaff and Wheeler, the cost is quite high. And so we started thinking, perhaps this creates an opportunity to leave this material in place and maximize habitat values and sort of evolve the design here with the reality on the ground. So this is a very simple schematic of the current working recommended transition zone design. It calls for leaving that bay mud stockpile in place. That would create about 350 feet of marsh because the elevation of that bay mud stockpile is capped out at 7 feet, which is pickleweed marsh elevation. And then backfilling the space between that stockpile and the flood risk management levee with imported fill using the free dirt market, which of course has its challenges, but nonetheless remains an important tool in the transition zone restoration toolbox. And the idea is it would take multiple years to backfill that space using the free dirt market. Some of the benefits of this design is it would create more marsh sooner. If you have to wait for that pond to accrete sediment to take advantage of this transition zone, then there's sort of a lost opportunity to benefit from the transition zone by creating more marsh sooner. You connect those two habitats sooner in time. We'd also construct a bay mud wave break at the toe of this slope, water could still come into the marsh, but it would break up the waves. It would probably last about a decade, and that would give a chance for marsh to get established at the on the marsh plain. Once those roots and vegetation are in place, that would help to slow the erosion of the marsh and give time for the outboard ponds to accrete sediment. And after, just say, I mean, we can look at different sea level rise scenarios, but let's say after 3 feet of sea level rise, the marsh would move upslope onto this transition zone. There would still be about 60 feet of upland between the tidal marsh and that adjacent upland habitat, which is sort of an ample buffer space for refugia. I'm not going to go into the whole revegetation design for the transition zone, but I want to just touch on some of the elements. The idea is to create a diverse, native habitat mosaic here. And we want to do that by creating a variety of abiotic conditions through things like creating micro watersheds on the transition zone slope to help focus water into specific parts of the transition zone. Because there's a broad marsh, there's an opportunity to create first order tidal channels and do revegetation of gum plant and start providing some in-marsh refugia within the marsh part of this transition zone. We would do plantings of species that don't recruit naturally on their own to create a diverse marsh. And above the high tide line, the idea is each year as soil comes in through the free dirt market and you get up to grade, you have an opportunity to revegetate without a large weed seed bank, especially if this is subsoil that's come from a construction project, maybe feet down. So the idea is once it's in there that very year, take advantage of it, seed it, and plant it, and do weed control to get a native plant community going and kind of work your way along the transition zone. So the second project I'm going to touch on is the Safer Bay project. This is being implemented by the San Francisco Creek Joint Powers Authority. And when it's complete, it'll protect 7 miles of shoreline in South San Francisco Bay. And similar to the shoreline project, it will enable restoration in collaboration with the South Bay Salt Pond Restoration Project. And this project calls for creating gently sloped transition zones wherever that's ecologically advantageous. We've started to explore where we think it might be ecologically advantageous down here, just at the southern portion of the reach. And I should just note that the pathway of this flood risk management levy system is still being worked out. So this isn't final. Okay, so under the scenario in which a flood risk management levy was constructed between Faber, Laumeister, and Ravenswood Open Space Preserve, and if it were to run along, the back end of those marshes against the developed habitat, the question is, would a transition zone make sense in this setting? And if so, what sort of width, what kind of slope? And to get at that, we first started by thinking about, does this marsh need refugia habitat? That's one of the functions that T-zones provide is refugia habitat. So we wanted to look to see, what refugia is there now, and then do sort of a qualitative assessment of if we think a broad T-zone would be beneficial. So this is a map showing just Faber and Laumeister marshes, the results of that refugia study. The light blue are gum plant lined slough channels where the gum plant is tall enough that even on extreme high tides, they can provide refugia cover. There's abundant in-marsh refugia at both of these marshes. And then we mapped the quality of the transition zone with high quality shown at the southern ends of these marshes and then low quality along the backshore of the marsh. And so these marshes are highly functional in terms of supporting wildlife. There's consistently high California ridgeways rail observations. And we think part of the reason for that is there is abundant in-marsh refugia in these marshes. If we were to extend the transition zones into these marshes, our opinion is that that would not benefit salt marsh harvest mouse and ridgeways rail because it would just, for example, if we were to do a 20H to 1V transition zone, that would fill about 10% of the study area marshes. So you'd lose 10% of this sort of highly productive marsh space initially, and there's already adequate refugia, being provided. So a second question is, but would transition zones benefit sea level rise accommodation space? So I'm going to show a cross section of what a 20H to 1V T-zone would look like, thinking through this question of, what would be the sea level rise accommodation value of a T-zone here. And this is showing with 3.5 feet of sea level rise that marsh would transgress upslope. And it would create about 15 acres of marsh, which is about 4% of the surface area of these marshes now. So in this scenario, if we imagine that with 3.5 feet of sea level rise, we lose our outboard marshes that are highly productive and functional, and we're left with 4% of our study area, the transition zone, we don't think that that's going to be enough to sustain the functions and values of these marshes, right? That we really need to, rather than putting a broad transition zone in these marshes, we think it's more important to, sustain the marshes and its in-marsh refugia to continue to provide the benefits that these marshes are providing now. So instead, for these marshes, we're considering, in the project description, which is still being developed, we're considering a narrower transition zone slope, more in the ballpark of 3H to 5H. This would reduce the footprint of impact on these marshes. And after 3.5 feet of sea level rise, it would leave a sort of a kind of a small to moderate buffer zone size of 12 to 22 feet, depending on that slope. And that would be a substantial improvement from what's there now. And while it's not as broad of a buffer as I think is ideal, it's preferable. It's a trade-off, right? And we think it's preferable to losing highly productive marsh for decades. So some key thoughts just to wrap up my slides. We're all aware of the benefits of transition zones, but I think it's also true that one size doesn't fit all. For the shoreline project, where we're going to be constructing a transition zone adjacent to open water, we think building a broad transition zone with substantial marsh has multiple benefits. It's going to slow erosion, and it's also going to bring marsh species that use the marsh to the area to benefit from the transition zone sooner than would be the case if you waited for accretion to form that marsh. And at the Safer Bay, just thinking about those 3 lower marshes along the study reach, and in that case, we think that sustaining that marsh is a higher priority than a broad transition zone. And then just want to kind of end with the thought that, and this is something that I feel like everybody knows, but in this talk, it somehow feels important to say, because we're all talking about the T-zone and what its value is and what its benefits are, and it has a lot, and it's great that it's being incorporated in projects, and it should continue to be incorporated in projects. But this is part of the complete marsh story, right? We need to have the marshes, we need to get them up to the right elevation and create in-marsh refugia. That's where we're going to get, the heart of the value for species and wildlife. If you imagine a transition zone here for the shoreline project, it benefits the species that are, within 200, 300, maybe 400 feet of that refugia space that's created on the transition zone. The rest of this marsh complex needs to have its own in-marsh refugia to support those species. And when you think about kind of how narrow, like this is a broad transition zone, it's expensive to build, it is a complex project. When you think about the size of this compared to the historical landscape that SFEI showed in the beginning, where you had miles wide space for sea level rise marsh transgression, it's a small space for marsh transgression. Like, we're not going to maintain the function of our marshes through constructed T zones at this scale. It's going to have to be by sustaining the marshes with sediment addition as part of that whole marsh concept. That's it. Thank you.
Thank you all. And we're doing a little bit of slide uploading on the fly. Stuart just got in this morning, last night. So we're going to be bringing his slides up now.
And I'll just say I'm time zones away at the moment. So it's been 24 hours on an airplane or airplanes. And they made an adjustment on the fly here this morning. So I'm going to build some on what you just heard from Steve and Gavin, and you're going to hear more from Peter Bay, I'm sure some others later today as well. So that's part of the adjustments there. And it will come up at some point, right?
That's the scan for malware. Yeah.
Right.
Should pop up.
So I'm gonna kind of talk a little bit about some of the big picture stuff and then how they get applied with a few case studies. One of them was Sears Point, and so Steve mentioned that. I tailored it back because Peter Bay has some more information about Sears Point. Yep, that's the one. And then really kind of think about how is I work a lot in the North Bay and Suisun and the Delta, and very different than the South Bay and the Central Bay, that we actually have some landscape, sort of, kind of, and some opportunities and some stuff called high marsh, which is very valuable as well. So.
Sorry, one sec. Mind? Just do this. Thank you all for your patience.
Perfect. Great. So I'm Stuart Siegel. I'm the interim manager of the San Francisco Bay National Estuarine Research Reserve, located at the Estuarine Ocean Science Center in San Francisco. And I'll just put a plug in from this morning's talk is in terms of bringing the next generation of folks into the kind of work that we do. The San Francisco State University and the EOS Center is what that does. So that's a great place to direct students out of high school for undergraduate and graduate. A lot of opportunity there. So we've had this nice conversation already, which about functions and values. And so I always ask the question, why are we doing this? And so there's really two things. Broadly is these variety of functions, and Gavin just covered quite a few, which is great. And I put over the long term, because we want to think long term, not just next 5 or 10 years, but going much further than that in the face of a lot of environmental change. And then there's a lot of attention, we've heard a lot today, and you're going to hear a lot more about one particular function, which is really great, which is how these natural systems can help protect the human-built environment. And that's these nature-based strategies. And so that's why we're doing this. And I'm glad that I have a little groundwork laid on some of the specifics of that, but I really want to emphasize the idea of the long term and the variety of functions that we're going to be getting out of doing wetland migration. And there's actually two kinds of migration. And this is, it was alluded to, Amy actually mentioned this morning, I want to emphasize it. What we heard about just now is there's horizontal estuarine transgression, it's called, and that's how this estuary was built. As sea levels came up, they flooded the river valleys and the edges, marshes built, the bayfront may have stayed put, it may have gone backwards. Where we have a lot of space where it's flat, like the very far South Bay, that's what used to happen. And now it's very constrained. You see that the Delta has a ton of that kind of very flat landscape, a lot of opportunity, sort of. Then the more limited around Suisun, where it's a steepish kind of slope, it varies a little bit. And then what most of you are used to, and we heard a lot about, is these very steep shorelines, levees, and hard shorelines, where you're basically up against a 2-to-1 or 3-to-1 or 5-to-1 levee, and make these choices. That Gavin just had a really nice approach to that. So that's the horizontal version. And then the other is the vertical, is that if our marshes can keep pace with sea level rise, we sustain a lot of marshes. And this is a work that Lisa Shilley did at China Camp about 10 years ago, comparing sediment concentration versus rate of sea level rise. And if we have slow sea level rise, lots of sediment, there's a good chance that marshes might sustain. Flip that around, low sediment, high sea level rise, they go under. And so strategies to maintain marshes in the vertical, same with humans, you can retreat laterally or you can retreat vertically. And you go to Asia, everything's on stilts, right? Or the Russian River, right? So there's different ways to think about that. The one thing I'll also mention is salinity matters, is that a lot of us deal with tidal salt marshes. The vegetation is up near the top of the tide, so you're really focusing on that little piece. The more brackish and freshwater you get, the plants can grow a lot deeper in the tidal frame. You get to the delta, and that picture on the bottom right, it's 10-foot tall vegetation that grows below low tide. And so the ability to provide these functions is really different based on where you are in the estuary. And these more brackish settings can apply to Coyote Creek in the South Bay, Napa River places, the tributaries, as well as in the Suisun and the Delta. So that really does matter a lot in some parts of the system. So I think about what are these kinds of changes we have to deal with, because they come in planning as well as stuff. And everything on my list is out of our control, right? So just keep that in mind. That's the idea of uncertainty, is we have no control. And so how fast these changes will arrive and how big, those are the two big ones. So sea level rise is a great example. Is there are always projections of these broadening arrows and everything. And the answer is we don't know, right? And it's coming. We don't know how fast. We kind of watch the news and look out the window sometimes and get a sense. So that's the challenge for planning. What do you pick? And then how many changes? It's not just sea level rise. We have warming, we have different nutrients, we have heat, hot water, all this kind of stuff. It's a lot of those things are going to come as well, not just sea level rise. And then what we do, I have an idea of action and inaction, which is global, but also very local in all the projects we do or don't do and regulations we change or don't change, how that promotes or ameliorates these kinds of changes. And then lastly, how these things interact with each other and how they interact with us. And back to the kind of the people in the element is there's a lot in there. And we have, the only thing we have control over is what we choose to do in response to these things, but the rest of it we don't. And so, and some of those choices we have are very difficult to make. A lot of talk about regulatory. So I've permitted a lot of projects and it's a challenge to say the least. And so every single law on the screen was written long before anyone thought about climate change. And all the statutes and regulations came out of 30, 40, 50 years ago. There's maybe one on here was thinking about it, which is the Delta Reform Act, maybe, right? And so, and then a lot of times, you know, the folks deal with regulation, you can't make regulations that don't have any basis in statute. And so going back and changing statutes, maybe in Sacramento, possible. DC, I wouldn't touch that probably, and no one has for a long time. So I wish and hope that the work that Britt does and others is very successful at doing everything they can. And we hope, because it is very challenged as to how to get things permitted. So what this leads me to is kind of the broad context is overarching approach is looking as far forward as we're able to do and all these uncertainties, follow natural examples as much as we humanly can. And you've heard a little bit, you're going to hear some more. I'll have a little bit. I have this thing called integrate techniques. And so rather than just one strategy, because if that doesn't work and you put your eggs in one basket, then oops. And so if you can blend things, if something doesn't work, something else does, hopefully. So there's a lot of blending of techniques in there. And then understand place and people. We heard some this morning. We'll hear some more about that, is how these things fit into the communities, where people live there, and also the geomorphic setting of all these places. And then from there is aim for the greatest likelihood of success. And so I just have a couple of pictures here of natural beaches. I think the picture on the upper left there is Foster City, I think. And then apply that to design. And one of the things that came up in the regulatory discussion already is beach construction is an example of dynamic fill, not static fill. So when we permitted some projects, it was hard because where we put that material in that upper right picture, it won't be there a week later. It'll be somewhere else. And how do you handle that in a permit? And we did, but it was not easy. And it's gonna, you want these kinds of systems is the ability in the regulatory context to be able to accommodate that. And so these cases of natural beaches, the driftwood, which Peter Bay will talk a lot about more with Sears Point, just look at these examples and apply them as much as it can be applied. So where you sit here, and I hate text slides, but I had to put one in here. So there's really sort of 5 kinds of contexts. What does your tidal edge look like? Are you on the open bay with a lot of wind fetch and waves? Are you up a big river? Are you up a small slough? Do you have watershed connection? What does your upland edge look like? We've heard some, we're going to hear a ton more today and tomorrow about this, and how steep, what kind of land use is there, is it managed or not? What kind of marsh? Like we work at the nearest China Camp and Rush Ranch, it's ancient marsh, it's high marsh, there's centennial marshes around the margins of the bay in some places, there's older, newer restorations that might be adapting, and there's of course all the dikes, baylands, mostly subsided. How wide are they? What are their elevations? What kind of vegetation is or isn't there? We all have to deal with tidal flood protection. You know, this is for years and years is don't flood thy neighbor. And so what that looks like, you know, at China Camp and Rush Ranch, there's no one to flood, sort of. Sometimes you have integrated levees like at Sears Point and many of the South Bay projects. Sometimes your project is just a little piece and once something bigger is done, you might have flood protection, but that project isn't building the whole thing. So Corte Madera, Ecological Reserve, Tiscornia Marsh and Santa Fe, these things being planned. There are segments of some future thing in theory. And then sediment supply, back to the vertical migration, is how much sediment is there? Where are you in the estuary? You think with sea level rise at big shallow mud flats, the deeper the water gets, the less energy for a wave of the same height to resuspend sediment. And so that sediment will become less and less available with sea level rise, assuming the mud flat doesn't change. And then do you have watershed sediment in the systems anywhere? So I'm gonna start with Rush Ranch because we have several restoration projects. And these are kind of unique. I'm not gonna talk much about China Camp, except to say that China Camp, back to the idea of community planning, is a very evolved process with the community. The same with Goat Island Marsh, which is just about to get underway. We built Suisun Hollow and Lower Spring Branch Creek a few years ago. So we're able to reestablish these natural migration spaces. Some are edges of the hills and some are up little stream valleys. So we got with Lower Spring Branch, which I'll cover more, we got 15 acres of tidal marsh, 14 acres of floodplain, and a mile of edge. So that's a lot in a pretty small project. And then Goat Island, which will be built probably a couple, 3 years from now, 80 acres of marsh, not quite a mile of upland edge. So there's opportunity in these kinds of places. And the thing about it, which I'll conclude with, is there are places this can happen, but they're behind levees right now. So when you think about the South Bay, think about Coyote Hills and these places where there's actually out of these edges behind a levee with a dike marsh, a salt pond, or whatever might be in front, and how you kind of handle that, take advantage of that. So in our Lower Spring Branch, we had the darker green is the tidal marsh of Rush Ranch. This pointer, it doesn't do anything. Okay, so the dark green is the tidal marsh. We had a ranch road with a couple little tiny culverts in it, had a muted marsh behind it, and then up into the seasonal floodplain of the creek there. And this is in some ways a kind of an easy fix, is how do you get more opportunity out of this, both up that seasonal floodplain, a nice alluvial basin there, and then use the edge of these hills where there's endangered plant species on there we want to promote. And so what we did here on the upper right is the old ranch road. You can't even see the culverts. They're just a couple little culverts. We ripped that out, put in a very large arch culvert, and arch culverts are great because you get a natural channel bed. And we built it. You can see the size of that compared to 2-3.5 foot culverts. It's up high, so a lot of sea level rise accommodation there. It's very large, so the ties can go in and out. We also lowered the ranch road either side of it. So when you have big flows from the creek, it just floods on the sides as well as not constrained to the channel. And that's a nice opportunity this place offered. And we got to test it this past winter because we had lots of rain. And then on the upper right is kind of looking at an oblique view of the marsh, is that we also dug about 1,200 feet of new channel in the marsh there to get the ties to go up further. And again, there's actually across the road, there's upper part of the creek there. So we got a lot of transition zone and migration space created with a relatively small project. It was not that expensive in the scheme of things. We had a little bit of fill in wetlands and waters of the US and the state with that arch culvert that we didn't have to mitigate for, fortunately. We had a lot of challenges with endangered species out there. And luckily, the day we were constructing, and there's a big salt marsh harvest mouse question, we were at a workshop a couple miles away with everybody, and we just drove out there and looked around, and the people from Fish and Wildlife and Department of Fish and Wildlife, state and federal, looked at it and said, do this. And the contractors did, and it was done. And that was lucky because we all happened to be in the same room and the phone call came in. So that's sometimes how things get done. But it was really critical to have that capability. The next example will be Sonoma Creek, and this is a centennial marsh in the North Bay, of which there's a lot around the estuary. And this is an interesting one because it accreted since the 1960s. So it's a new centennial marsh. And what happens, especially in the North Bay, and the South Bay is similar, but not quite as extreme, is there's no tidal channels on the bay edge. It's basically a natural high berm. It creates these depressional basins. South Bay centennial marshes have a little bit more of a channel in there than the North Bay does. And on the picture on the right, you can see this big barren area. And this is this exact same thing occurs on the strip marsh along Highway 37 between Sears Point and Vallejo. We're just going now on a very similar project that we did at Sonoma Creek over there. So these areas this is Tubbs Island, Vallejo Sanitation. There's biosolids reuse there, a sketch old levee. You guys have seen those kinds of places. No habitat, no transition zone. The mouse was drowning, major mosquito production. The Mosquito Abatement District was a huge sponsor here. And no refuge space hardly anywhere at all. And so this is, how do you handle this kind of situation? And so what we did here was cut a very large channel, this big yellow channel from Sonoma Creek. So rather than being on the bayfront, which would fill in quickly, it's around the corner. It'll still fill in, hopefully more slowly. A lateral channel connected to some really poorly draining areas near the levee. Then we have a transition ramp, which I'll show pictures of in just a minute. And this is our transition zone. It was about a 50-to-1 slope on there. So a lot of habitat, fill in wetlands and waters of the US. And we also had thin layer deposition was also permitted here, which is fill in wetlands and waters of the US to do small lateral channels. And then marsh mounds. So about 50,000 yards of dirt came out to dig that channel. A bunch of it got used to make a bunch of marsh mounds, fill in wetlands and waters of the US. that were they become revegetated, mostly high marsh, but some transition species there. And the rest of that got used for transition ramp and some other levee maintenance work out there. The challenge of these places is that these are flood tide systems. As the tides come up that channel, they're really designed to drain that ponded water so that the vegetation can come back. And you still have the problem with that outboard with the natural berm, not letting the high tides in, so less overbaked tides. So this was planned knowing that channel will fill in over time and it will have not a super long-term longevity, but this is where sea level rise might help keep that channel going there. And I'll just show you the sense of this transition zone berm. So that bright green on the left in the map there is that transition ramp, about 50-to-1 slope. The upper right is when we built it in 2015, very broad, very covered in mud. Within a year, it was pretty vegetated. The lower right photo is 3 years later. You can't even see it anymore. And then even now, it's marsh and a little bit of transition zone and not too many upland weeds, which is really great to know. And there was, I think, straw went out and did some planting out there. So this is the kind of thing that very similar to what we heard about before is, can you make these things, can you build them into your projects? Here, we already had a high marsh platform. The idea of when you deal with areas that are 6 feet below high tide level, you're trying to build it back up. That's a lot of sediment or dirt import or whatever it may be. These places are already those nature-based shoreline protection systems. You just want to keep them functioning and then deal with the edge. And so along 37 with the strip marsh, it'll be the same idea. And what to do with the edge along the highway will be an interesting thing, is how to do that. And that's upcoming very soon, actually, what that design of how to make that look. Next, I'll talk about Sears Point, and I'll be a little brief here because Steve covered some and Peter Bay will cover more. This map on the right was the design, was what got built there. So that north levee, as Steve mentioned, had a 10-to-1 to 21 slope. It was a flood control levee, had the habitat levee, had the small pans that Steve mentioned on there. The west levee separates the project from some baylands, which, if you think about it, you're separating one restoration from another. And then the lower left there, let's see, these dredge ponds. So the very bottom, they dredge a channel out to deeper water so we get good tidal exchange. All that material went into the brown area, the southern part of that western levee, which was unfortunate if it got to the northern part, which got public access preservation for BCDC, and then began eroding away. Where the dredge material got put, there was no erosion of that levee. It's worked wonderfully. But if they just moved it north, it would have saved a little bit of effort. But that's how things go. And then these marsh mounds, as Steve mentioned, about 500 of them, and they were intended both as a wind wave diffraction system and as a huge nuclei of marsh establishment. So instead of just a bathtub ring of marsh coming in, you had that plus all these points of marsh also expanding outward. The trick, though, is the design is intended was don't breach until you've got the place covered in vegetation. So give it a couple of years as a diked marsh. That was omitted. And so you can look on the left, the northern and western levee were freshly graded and straw and all that kind of stuff. And then a few years later, they were just clobbered. And then all those marsh mounds are gone. They got all wiped out within the first couple of years. And a grad student at SF State, Margot Buchbinder, did her master's on it. And she had this whole different project in mind, and she watched them disappear. And she worked with Invasive Spartina to come in and plant them. And they're actually some are there, but of those 500, only the ones in the very back corner that didn't have that wind wave energy survived reasonably. So we had the scarp we had to deal with, which led to an adaptive management project to fix this. And one of the things you can see in the lower right is you would get marsh forming, and then you get some storms and it would all get scraped away again. So it was start, stop, over and over again. Very vertical scarp in this whole system there. So working with myself and Peter Bay and Roger Leventhal, we came up with a design that had lots of elements in it. Peter's going to cover this a bit more. There was physical elements into it. We had some grading. We used large wood, some planting, some mud, some gravel. But also we built in physical process elements. So we placed on that slide ahead of the beach, we placed dried bay mud and gravel with the intention that it would be moved around by the tides. It would also be stabilized by vegetation as well. So we're relying upon these natural processes to give us where we wanted to go. And so I took out a couple of slides as my adjustments since Peter's covering them. So this is kind of a picture of what things look like. We had on the left picture of the very lower edge, we had a brush fence in a couple areas because we had more erosion there. We had almost 300 logs out there. We had a gravel tow berm to become a beach. We put a bunch of, in the upper right, we put a bunch of bay mud out there, which came from Port Sonoma. Material sourcing is reuse old dredge material. All the logs were from utility line clearance or fires. The only thing, the gravel was a creek dredging flood control in Sonoma. The only thing that was purchased was the cable anchors that hold the logs down. Everything else was reused nearby or from somewhere relatively close by. And all the logs got donated by Caltrans and PG&E, so that was really helpful. So all these pieces put together, combination, this is where you sort of spread your eggs around multiple baskets in case something doesn't work. And I think I have a picture here. So we have a grad student now who's doing her master's on how it's going. And so you can kind of skip the upper left. You can see one of those logs surrounded by vegetation. She's out there doing her vegetation transects. We went from an eroded scarp of nothing to an incredible amount of vegetation that's coming back beautifully. And this is, the upper pictures were just from last month. So it's really worked well. And up at the bottom picture, this is a reminder of what that looks like. And the last thing I want to cover, which is I took out but I put back in, was the idea of these natural edges. And so when Sears Point got, this is the time thing looking forward. When most of this land in blue, this is a digital elevation model. So everything in blue is subtidal. And then the greens are kind of tidal edges. So this is where Highway 37 is and everything that when they were looking at buying that property, a lot of opportunity, this great upland edge, a lot of upland edge. With constraints. We had Highway 37, Lakeville Highway, and at the time was a decrepit railroad that wasn't in use. It was falling apart. And what happened though was that between the time the property was purchased and the time restoration got going, the railroad came in and rebuilt their thing in place below sea level and said, well, if you want to get us out of the way, it's $50 million. And so this applies to the entirety of the Napa Sonoma marshes, anywhere. If you can get in ahead and work with the infrastructure entities so they don't spend money and block you from doing something, then you have an opportunity there. And there's a lot of this in the North Bay and Suisun to try to really get around that kind of limitation. And so there's a lot. So we could have had a lot of transgression, but it's now behind a $50 million railroad. So with that, I'll say thank you very much.